Hi there. So this video is designed to give you a little bit more practice, or just to hear me say again how to compute the domain of a composition of functions. The domain is equal to, whenever you're working with composition of functions, it's equal to the overlap of the domains of the interior function with the resulting function. And what I mean by interior and resulting function, what we'll talk about in just a minute here. Composition of functions can be represented in one of two ways. As I mentioned to you in the content video, that it's f followed by g of x. And it kind of looks like fog. In MyLab Math, they tend to use this notation more than this one over here on the right. I typically do, though, use the one over here on the right, but it means the same thing, is that this f followed by g of x is really f of g of x. And so what I'm talking about when I refer to the interior function, that's the function here on the inside. This would be, I always tell you, and I told you before, like you work from the inside out. This is your interior function. So you're going to be finding the domain of, for these, you'd be finding the domain of g, and then you would find the overall domain of f of g of x, and wherever those two overlap, that's going to be your final answer. Another combination, g followed by f of x. So here, your interior function, remember this just means g of f of x, then my interior function this time will be my f of x. And I will find the domain of f of x and see where it overlaps with my overall result that I get, okay? So I've got two examples that I pulled here for us to look at. So here in example 1, you're given an f of x function, f of x equals x squared minus 10, and g of x equals 3x minus 4. Now recall, whenever you are looking at your domains, the only time you have any kind of restrictions to your domains is if you have a square root or if you have a letter in the denominator. In the case when you have a square root, get a different color here, in the case where we have a square root, then remember that argument underneath the square root needs to stay positive. So that argument there needs to be set greater than or equal to 0, and you solve for x, okay? And then likewise, I'll just put, like, you'll have some number. If you have a denominator, with your function, then you have a restriction there because the denominator cannot equal 0. So you set your denominator not equal to 0, and you solve for that x. And so then that ends up telling you, okay, well, this is what your denominator cannot equal. This is what the function cannot equal. These are your restrictions for domain. That's what you have. So if you don't have a square root in your function and you don't have a letter in the denominator, then you don't have any restrictions to the domain, and the domain will always be negative infinity to positive infinity. So when I look up here automatically at my f of x and g of x, I see that I don't have a square root, as well as I don't have a letter in my denominator. Furthermore, let's just do one more thing here with these two functions, just to kind of before I say that, because they don't have either one of these scenarios, no square root, no letter in the denominator, the domain for both of these should be all real numbers, negative infinity to positive infinity. Another way to look at this is that, remember, when I say domain, we're just worried about our x's. Another way to look at this, though, would be to graph it. So if I looked at the graph of f of x, I'm just going to crank out a rough sketch here. The graph of f of x, this is y equals x squared minus 10. You could put this in your calculator. You would find that it looks something like this. So you've got a parabola here. We'll talk more about parabolas later on in this unit. But what we can see here from this graph is that this graph goes up and to the left forever, so it's going to the left forever. It goes up and to the right forever. So since it's going left and right forever, then we know the domain of f of x is negative infinity to positive infinity. G of x. Let's crank out its graph real quick. Okay, this was in our last unit. This should be very recognizable to you, that this is a slope and y-intercept. So if I were to graph this line, I would have a y-intercept down here at -4, and then it's up 3 over 1. So I'm just doing a rough sketch. Okay, so you have a graph looking relatively something similar to that. This graph is going down and to the left forever, so it's going to the left forever. It's going up and to the right forever, so it's going left and right forever. So g of x also has a domain of negative to positive infinity. Okay. All right, so I just wanted to kind of, that's just a quick recap of just domain of what we've talked about up to this point, okay? Now we're stepping it up a notch whenever we start looking at our composition of functions, because we have to look at two items in order to get the overall domain. So let's first find, in letter A here, it wants us to find f of g of x. So with our composition of functions, we work from the inside out. So g of x, we find that first. That's given to us. G of x is 3x minus 4. And so remember, this says, okay, now go to your f function. Everywhere you see an x, plug in 3x minus 4. So f function, I see an x, so I put in 3x minus 4, all squared, minus 10. So remember, this is in parentheses squared. It's not legal just to take 3x and 4 and square them. This means that you have to write this twice and FOIL it. Anytime you have something in your parentheses with an addition or subtraction sign, you've got to write it however many times your exponent is up here, and then FOIL. So 3x minus 4 times 3x minus 4, and then I still have my minus 10 out here. So now when I go start to FOIL, 3x times 3x, 9x squared, outside 3x times negative 4, minus 12x, inside negative 4 times 3x, minus 12x, negative times negative, positive 16, minus 10. One more step, we'll combine like terms. So I have my 9x squared, negative 12 and negative 12 give me negative 24x, positive 16 minus 10 give me a positive 6. So this is f of g of x. Okay, so we found that piece. Now, to get the domain, as I mentioned to you up here at the top, the domain is the overlap of the interior function with the resulting function. So your interior function is your g of x. So the domain of g of x, and I already, we already discovered that already, okay? Because g of x is right over here. This is the graph of g of x, and we said, okay, it's going left and right forever. It didn't have a denominator, it didn't have a square root in it, so it does not have any domain restrictions. The domain of g of x is negative to positive infinity. Then I also need to look at the domain of my result. The domain of my result, when I'm speaking about the result, I'm talking about f of g of x. I'm talking about this function right here. So looking at this function, it doesn't have a square root in it. It doesn't have a denominator. So what does its domain have to be? Hopefully you agree with me. Negative infinity to positive infinity. Okay. So now the overall domain, the overall domain of f of g of x is equal to the overlap. I'm just going to write it over here, is equal to the overlap of these two pieces right here. It's equal to the overlap of these two pieces right here. Well, if they're both negative to positive infinity, then they are going to overlap everywhere. So the domain of f of g of x is negative infinity to positive infinity. And that would be your final answer for the overall domain of f of g of x, okay? You'll see something different in the next example, okay? Not on part B here, but on the next example that I've chosen. Okay. All right, so let me scoot on down here to, it will let me. Scoot on down here to letter B. I want to find g of f of x. So I'm still sticking with the same functions up at the top, working from the inside out. So g of f of x. So f of x was x squared minus 10. Now this says go to your g function. Everywhere you see an x, plug in x squared minus 10. So I have, go to my g function. So I have 3, I see an x, so parentheses, x squared minus 10, and then I have my minus 4. Take that 3 and distribute it. So 3x squared minus 30 minus 4. And so then that gives us 3x squared minus 34. So that is g of f of x. Okay. Now let's again look at the domain. Remember the domain. I want the domain of the interior function. So this time interior function is f of x. f of x, if we go back and recall, f of x is x squared minus 10. We already graphed it. We said, you know, it doesn't have a square root. It doesn't have a letter in the denominator. So my domain here has to be negative to positive infinity. Domain of my result. Remember, this is your result up here. It doesn't have a square root in it. It doesn't have a denominator. You don't have any restrictions. Then again, domain has to be negative to positive infinity. So then domain of f of g of x is where these two overlap. Overlap of these items here. They're going to overlap again everywhere, so that's equal to negative infinity to positive infinity. Okay. All right, let's flip it over then on this next page, and I've got a different example here for you, just so you can see something, you know, see some restrictions happening to your domain. So here you're given an f of x function and a g of x function, doing the same thing. So working from the inside out, f of g of x, so f of g of x is 1 over x. Now this says go to my f function. Everywhere I see an x, plug in this 1 over x. So here's my f function. So 3 over, on the bottom I have 1 minus 7. Oh, I see an x. I'm going to be plugging in 1 over x. All right, keep cleaning this up. So 3 over, and then on the bottom I have 1 minus. This is like 7 over 1. So when you multiply fractions, you just multiply straight across. So 7 times 1 on top, 1 times x on the bottom. Now here's what's referred to as a complex fraction, because you have a fraction within a fraction. You can't leave it like that. So the easiest way, I mean, there's a couple of ways. You can get a common denominator down here and then copy, change, flip. I find it easier just to multiply by the common denominator. You'll get there a lot quicker. So the common denominator is, you're just looking for whatever the common denominator is in the denominator. So here, the only fraction you have in the denominator is x itself. So I just multiply every term by that x. So up top, 3 times x, 3x. On the bottom, x times 1, that's x. And then for this last term, these x's are going to, I'll just come over here to the side. When I'm going to take 7 over x and multiply it times x, think of this as like x over 1, those x's are diagonal, so they cancel out, and that just leaves me with 7 divided by 1, or just 7. So that's the reason why you multiply by your common denominator, because then you're going to get rid of the denominator. And so then that is f of, so we can say then that f of g of x is equal to 3x over x minus 7. All right, so that's the first part. Now we need to focus on the domain. This domain is going to be a little bit more involved. Domain of interior function, right? So you need, remember, for these composition of functions, you need the domain of the interior. So in our case here, we want g of x, so the domain of g of x. We go back and we look at our g of x function. Oh, this time I have a letter in the denominator. That denominator cannot equal 0. So whatever is in the denominator, here it's just an x, you set it not equal to 0. And if we could, we'd solve for x, but we can't solve for x. It's already solved for us. So essentially, it's already telling us then that our domain is everything but 0. So what that means then is that I can write this in interval notation as negative infinity to 0 union 0 to infinity. And you know what might be helpful here is to graph 1 over x, just so you can see that in your calculator. So if you go to graph 1 over x, I don't think I will turn my the graph of g of x looks like this. Got That's the graph of g of x. So you can see that it hugs this y-axis. It gets really, and it hugs the y-axis down here. It gets really close to 0, but it never actually equals 0. So that's how we can identify our domain also, is looking at the graph, because remember the graph, you're only reading your x-axis when you're talking about the domain. So this hopefully gives you also a visual for the domain of g of x. All right, so now we're not done yet. We have to intersect it with the domain of the resulting function. So I also need to now look at the domain of f of g of x. So the domain of f of g of x, look at it. Oh, I've got the denominator here. It can't equal 0. So I take that denominator, x minus 7, and say, okay, you cannot equal 0. I need to figure out what that x value is. So I could do this in one step. I want to solve for x, so just add 7 to both sides. So here we see x cannot equal a positive 7. So converting that to interval notation, that means that your x can equal anything but positive 7. So you have negative infinity to 7. And unite that with 7 to infinity. So now from here, we want to look at, I'm going to put this on a number line for you. And wherever these two overlap, that is your overall domain. So we know we've got a problem here at 0 and at 7. So I'm going to use two different colors here. So at 0, we know we can equal anything but the 0. So I've got parentheses on either side of 0, shading both ways. And then at my 7, can't equal that to there, but I can equal anything else, shade both ways. And then anywhere this shading, the red and green lines for me, are on top of one another, they get included as part of my final answer for the domain of f of g of x. So overall domain of f of g of x is equal to the overlap that you're seeing up here, okay, in this number line here. So we can see that red and green are on top of one another from negative infinity to 0. Then again from 0 to 7. And then again from 7 to infinity. Okay, and that would be my overall domain there for f of g of x. Okay. All right, we'll move on down then. Let's work this the other way. Let's find g of f of x and state its domain. So for g of f of x, here f of x is 3 over 1 minus 7x. Now this says go to your g function. Everywhere you see an x, plug in this 3 over 1 minus 7x. So you have 1 over, and then you have that, 3 over 1 minus 7x. Can't leave a fraction within a fraction here. I think here, what I would just do is I would copy the top, change it to multiplication, and flip the bottom. Because it's a fraction, you've got a top divided by a bottom and a fraction, so you can think of this as 1 over 1 up top. Copy the top, change the multiplication, flip the bottom, so 1 minus 7x over 3. And then when you multiply straight across, 1 times the top is still 1 minus 7x. And then on the bottom, 1 times 3, of course, is 3. So we now have gotten to a point where we know that g of f of x is equal to 1 minus 7x all over 3. So again, to find my domain, I need the domain of the interior function. So at this time, the domain of f of x. So our f of x function, recognize this was your f of x function was right here. So that means then that 1 minus 7x down there, that's the problem. I've got an x in the denominator, so 1 minus 7x cannot equal 0. You're only concerned about denominators if you have a letter in the denominator, okay? So a variable. So now to solve for x, I subtract 1 from both sides. Negative 7x cannot equal negative 1. Divide by negative 7. X cannot equal 1/7. So it's just a fraction this time, but it converts to interval notation in the same way that I'm going from negative infinity to 1/7. and then 1/7 to infinity. That would be the domain of f of x. Now I need to look at the domain of my result. Remember, that's your g of f of x. G of f of x. Now when you look at your g of f of x here, notice what happens, that you don't have, you do have a fraction here, but this fraction, the denominator doesn't have a letter in it. So this doesn't have a restriction. It's only if you have a letter in your denominator. So then that means that the domain of my result here is negative infinity to positive infinity. Furthermore, in case another way to think about this g of f of x up here, another way to write that is that both of these terms up here are divided by 3. So this means 1/3 minus 7/3 x. Hopefully then that should give you your clue here that you're looking at slope and y-intercept. The number in front of x is your slope, and this is your y-intercept. Now granted, they're fractions here, but this is still like a y equals mx plus b. So if you were to graph this, this is a looks something like that. So it's going left and right forever, negative infinity to positive infinity. So now we want to figure out, well, where do these two graphs overlap? So if I put them on the number line, so the first one has, I'm just going to put a 0 here. The first one has 1/7 as the hiccup. So I'm just going to exaggerate this 1/7. We know it's a really small number, but we're going to put that 1/7 right there. And I know that I can't equal the 1/7, but I can equal anything else. And then the bottom restriction says that I can go the entire number line. So here, my overall domain will be where those red and blue lines are on top of one another. And so hopefully you agree that that's everywhere but at the 1/7. So I can say then that my domain here is negative infinity to 1/7 union 1/7 to infinity. Okay, that would be your overall domain here for this function. So hopefully this helps give you a little, a few extra examples for domain of composition of functions. If you need anything else, let me know. Thanks a lot.